Hello everyone. In this lesson, we're going to talk about confidence intervals and how to create them using Python. Now, to this point in this guide, we focused on functions and syntax necessary to manipulate, explore, and describe data. Cleaning data and exploratory analysis are often preliminary steps toward the end goal of extracting insight from data using statistical inference and predictive modeling. The remainder of this guide is going to focus on analyzing data and tools for carrying out analysis in Python. Now, statistical inference is the process of analyzing sample data to gain insight into the population or distribution from which the data was collected, to investigate differences between data samples and the population that it was drawn from. In data analysis, we're often interested in the characteristics of some larger population, but it's not feasible to collect data on every single member of the population, so we have to use samples and use those as stand-ins for the population as a whole. For example, leading up to US presidential elections, it could be very useful to know the political leanings of every single eligible voter, but surveying every voter is not possible. Instead, we could take a poll of some subset of the population, such as 1,000 or 2,000 registered voters, and then use that data to make inferences about the population as a whole. One basic form of sampling inference we can use is a point estimate. A point estimate is just an estimate of a population parameter based on the sample data. For instance, if we wanted to know the average age of registered voters in the US, we could take a survey of registered voters and then use the average age of the people that respond to the survey as an estimate or point estimate of the average age of the population as a whole. The average of a sample is known as the sample mean. Now, the sample mean is usually not exactly the same as the population mean. This difference can be caused by many underlying factors such as poor survey design, biased sampling, or just the randomness inherent of drawing a random sample from the population. So we're going to start by investigating point estimates by generating some random age data and then drawing samples from them and looking at it. So we're going to start by generating some random data which will compose our population, and then we will check the mean or average age of the population. So you don't have to worry too much about what the actual functions are doing. We're just drawing some random values from the Poisson distribution. We covered that in the previous lesson. The average age of the population that we generated here is about 43 years. Now you can see here that we generated 250,000 data points. So that's a fairly large population. If those were actual people, it would be pretty hard to survey every single one of them. So if we wanted to get an idea of what the actual underlying average age was, this 43, well, we might be able to do that pretty closely by taking a sample. So let's look at how we would take a point estimate of this value and see how close it is to the real value. So to do that, we can use np.random.choice and choose to sample a certain number from the population. So we'll say np.random.choice. That's drawing from a sequence, so we're going to draw straight from our population here. So we're saying we want to draw from population ages, and we're going to draw a sample size of 500 people. Then we're just going to print the sample mean here, and also the difference between the actual mean and the sample mean. So when we run this, we can see that with our sample, we got an average of 42.3 years, and that's a difference of about 0.6 years from the actual underlying average of the population. So this illustrates the point that with a sample of only 500 individuals, we were able to get a pretty accurate estimate of what the underlying population average was. Now, another point estimate that might be of some interest is the proportion of the population that belongs to some category or subgroup. For example, we might like to know what the races of each of the voters we poll are to get a sense of the overall demographic breakdown of the voter base. So you can make a point estimate of this sort of proportion by taking a sample and then checking the ratio within the sample. So I'll give an example of doing that below. So we're going to start by assigning some different race categories here with different counts. There'll be 250,000 of them again. Then we're going to draw a sample of 1,000 different entries into this data. So we can use random.sample to do that. We're going to do a random.sample of this data. And then for each different race entry in this data, we're just going to print out what the actual proportion of that race is in the data set, which we know here. For instance, white here has 100,000 entries out of 250,000 total. And we're just going to compare that to the breakdown we get in our sample of 1,000 people. So in this case, for this data set, the underlying proportion for white should be 40%, 20% for black, 20% for Hispanic, and 10% for Asian and other. So when we run this, we'll see what the actual sampling proportions are, and we can compare those to the underlying proportions. So we can see that our sample of 1,000 people from this data set found proportions that are close to the underlying proportions of the whole data, but they're not exactly the same. We can see, for instance, that the white proportion estimate from our sample is 37.9, but the underlying proportion was 40. Now, in statistics, many procedures assume the data you have follows a normal distribution, because the normal distribution has nice properties like being symmetric and having the majority of the data clustered within a few standard deviations of the mean. Unfortunately, with real-world data, it's often not normally distributed, and the distribution of a sample from a data set tends to mirror the distribution of the population itself. This means a sample taken from a population with skewed data is also going to tend to be skewed as well. Let's investigate this by plotting the data we generated earlier and also the sample and checking the skewness. And if we scroll down here, we can see that while there isn't too much skewness, it is actually a bimodal distribution. So while the overall population average age was something like 43, that's actually not a very common age at all in this data set, because there are two centers here, one that's maybe around 28 or so, and one that's more like in the low 50s. So when we draw a sample from this population, we're going to end up with something with a similar skew and distribution. So we're just going to illustrate that here by doing the same thing, but on our sample ages this time. And we should see something relatively similar, fairly low skewness. And again, we see a bimodal looking distribution. It's a little bit more jaggedy because it's a sample, but it looks pretty much the same. Now, the fact that this data is clearly not normal suggests that we can't apply the techniques that assume a normal distribution to this data set because it's clearly not a normal distribution. But in reality, it is possible to still apply such techniques thanks to the central limit theorem. The central limit theorem is one of the most important results in probability theory that serves as the foundation of many methods of statistical analysis. At a high level, the theorem states that the distribution of many sample means, known as the sampling distribution, will be normally distributed, even if the underlying data being sampled from is not normally distributed. As a result, we can treat the sample mean as if it were drawn from a normal distribution. To illustrate this point, let's create a sampling distribution by taking 200 different samples from our population and then making 200 point estimates of the mean. We will then take each of these 200 point estimates and plot them to show that the distribution of these point estimates of the mean actually approach a normal distribution, even though the samples are being drawn from data that is not normal. So to do that, we're just going to initialize an empty list to hold our 200 point estimates. We're going to make a for loop that does 200 iterations. For each iteration, we are going to sample from our population, again, with np.random.choice, a size of 500. And for each of those samples, we're going to append a point estimate into our list here. And then we will take our point estimate list, make a data frame out of it, and create a density plot of it so that we can see the overall shape of the distribution of these 200 sample means that are sampled out of a distribution that is not normal. So let's run this and see what the result looks like. And we can see here that even though we're sampling from a distribution that is bimodal, when we take 200 samples from it and plot the density curve of the means of each of those samples, we get something that looks roughly symmetric and very similar to a normal distribution. In addition to the sampling distribution being roughly normal, The average of the sampling distribution approaches the true population mean. So if we take the true population mean and take the difference between that and the average of our 200 point estimates, we will see that the difference here is going to be smaller than it was with a single point estimate, because when we take 200 different samples and average all of those point estimates together, we end up with a better overall estimate. So we can see that now with 200 different samples, we are only off by 0.8 years if we average all those samples together. Now, point estimates can give you a rough idea of a population parameter like the mean, but estimates are prone to error, and taking multiple samples to get improved estimates may not be feasible. It might be hard to take 200 different surveys of 500 people. A confidence interval is a range of values above and below a point estimate that captures the true population parameter at some predetermined confidence level. For instance, if you want to have a 95% chance of capturing the true population parameter with a point estimate and a corresponding confidence interval, you'd set your confidence level to 95%. Higher confidence levels result in wider confidence intervals. You can calculate a confidence interval by first taking a point estimate with a sample and then adding and subtracting a margin of error to create a range. The margin of error is based on your desired confidence level, the spread of the data, and the size of your data sample. The way you calculate the margin of error depends on whether you know the standard deviation of the population or not. If you do know the standard deviation of the underlying population, the margin of error is equal to z times sigma over square root n, where sigma is the population standard deviation, n is the size of your sample, and z is a number known as the z critical value. The z critical value is the number of standard deviations you'd have to go from the mean of the normal distribution to capture the proportion of the data associated with your desired confidence level. For instance, we know that roughly 95% of the data in a normal distribution lies within 2 standard deviations of the mean. So we could use 2 as the z critical value if we wanted to make a 95% confidence interval. It's actually a bit more accurate to use a z table to find your critical value, or use stats.norm.ppf to check a critical value, than just to use something rough like 2, because it's not exactly 2, it's more like 1.9 something. But if we use 2, that would provide roughly a 95% confidence interval. So I'll give an example of how you could go about calculating a confidence interval for a sample from our population data we generated earlier. So we're going to start by drawing a new sample from the data. So we're going to say np.random.choice from our population ages. This time we're going to use a sample size of 1,000, so size is going to equal that. And then we will get the sample mean just by running .mean on our sample. So to get the z critical value for our 95% confidence interval, we could just use the shorthand of 2 for 2 standard deviations, but to be a bit more accurate, we'll use stats.norm.ppf with a Q of 0.975. Basically what this is extracting here is how many standard deviations above the mean do we have to go so that there's only 2.5% of the data beyond that. Now we're using 0.975 here instead of 0.95 like you might expect for a 95% confidence interval, because we're interested in errors that are both too far above the mean and too far below the mean. Then we will get the population standard deviation just by taking our age data and running .std on it to get the standard deviation. Next we will calculate our margin of error. That is using the formula we saw above. So we'll just take that z critical value that we calculated. We will multiply that by the population standard deviation, that was sigma in the formula above, and then divided by the square root of our sample size. And finally, to calculate our confidence interval, we can just take our sample mean, subtract the margin of error from one side, and then take the sample mean and add the margin of error from on the other side. So that will result in an interval where our sample mean is at the exact center of the interval, And this should capture the true population parameter or population mean with a 95% probability. So we will run this and show what our different values are here. So the z critical value we extracted with the stats.norm call was 1.95, so pretty close to 2 standard deviations. And our confidence interval was 41.7 to 43.3 years. Now, if we recall from when we originally created the data, the actual underlying population average here was something like 43.0 years or something like that. So this confidence interval does capture that population mean because 43 is within this range. So now let's create several more confidence intervals and plot them to get a better sense of what it means to capture the true population parameter, or in this case, the population mean. So all we're going to do here is just create a for loop that's going to run 25 times. And inside each iteration of the for loop, we're going to do the exact same thing we did above. We're going to take a sample, find the mean, get the z critical value, and calculate the confidence interval for that sample. And then we're just going to append that confidence interval to a list of confidence intervals that we're building up here. So we'll come down here and plot these 25 confidence intervals against the population mean. So we're going to use an error bar plot for this, and we'll plot a horizontal line where the true population mean is. So when we run this, we can see that each of these error bars represents a different sample and a different confidence interval. And we can see that for most of these confidence intervals, the red bar, which is the true population mean, does overlap with the confidence interval. For instance, our first sample here, the sample mean was a little bit higher, but our confidence interval was wide enough that the red bar lies within it. Now we can see that there is one sample here where the sampling mean was higher than usual, and the confidence interval that we created did not actually capture the population mean. Since we used a 95% confidence interval, that means the width of this interval here is wide enough that we'd expect it to overlap with the population mean about 95% of the time. Well, since we drew 25 samples here and did a different confidence interval for each one, we would expect to have one or two of them not overlap the population parameter, because 5% of the time, our confidence interval at a 95% confidence level isn't going to include the actual underlying population parameter. Now, for this example, we knew the standard deviation of the entire population, so we were able to use the z-score to help us calculate the confidence interval. If you don't know the standard deviation of the population, you would have to use the standard deviation of your sample instead of the standard deviation of the population when creating your confidence interval. But since the standard deviation of your sample might not match the standard deviation of the population as a whole, you're going to end up with more error in your estimate. To account for this additional source of error, in that case, we use what's known as a t critical value instead of the z critical value when creating the confidence interval. The t critical value is drawn from what's known as a t distribution. It's a distribution that closely resembles the normal distribution, but it gets wider and wider as the size of the sample gets smaller. So basically, when we have a smaller sample size, we're less certain about what the actual standard deviation of the underlying population would be. So we end up with a wider distribution that is more conservative and that will give wider confidence intervals because we're not as sure about the actual standard deviation of the underlying population. The t distribution is available in the scipy.stats library with the nickname t. So we can get t critical values using stats.t.ppf. So to illustrate, we're going to take a new smaller sample and then create another confidence interval without the population standard deviation, instead using the t distribution. So we'll give an example of doing that here. We're going to take a sample of only 25 values this time. So np.random.choice with a size of 25. We will again take the sample mean of that. And this time we're going to use a t critical value instead of the z critical value to calculate our confidence interval. So to do that, we can say stats.t.ppf. Again, we want to do a 95% confidence interval, so we're going to set Q equal to 0.975 again. But we also have to add this additional argument, df, or degrees of freedom, equals 24. That's telling the t-distribution that we have a sample size of 25. The degrees of freedom is the sample size minus 1. Then the rest of the calculations are basically the same. We will get the standard deviation of the sample this time instead of the standard deviation of the population. And we will get our margin of error by taking that t-critical value and then multiplying it by the sample standard deviation divided by the square root of the sample size again. That will give us the margin of error we can use to create our confidence interval. So again, we'll just take our sample mean, minus the margin of error and plus the margin of error, and we'll run this and see what our result is. We can see that our t-critical value was a bit larger than the z-critical value we used before. That's going to cause the confidence interval to be a bit wider, and the actual confidence interval is from 37.6 to 48.1 years. So between the t-distribution and the different standard deviation, it casts a much wider net and has a larger confidence interval. Now, as the size of your sample increases, the difference between the t-critical value and the z-critical value becomes smaller and smaller. So if you have a large enough sample size, there isn't really much difference between using the t-distribution and the z-critical value. Now, although thus far we've been calculating confidence intervals for point estimates by hand as a way to explain what confidence intervals are, you can actually calculate confidence intervals in Python automatically using the stats.t.interval function. So we'll show how to calculate the same confidence interval we just did manually using that function instead. So we could have said stats.t.interval. We want our alpha, or confidence level, to be 95%. So we would set that alpha argument to 0.95. The degrees of freedom, again, is 1 less than the sample size. So we would say degrees of freedom 24. You set the argument loc equal to your sample mean. And then the scale is equal to your standard deviation estimate, sigma. Now, the standard deviation estimate is different than the sample standard deviation. It's actually the sample standard deviation divided by the square root of the sample size. That's what sigma is here in this case. So when we run this function, we should get the exact same confidence interval we calculated by hand. Now finally, we can also construct confidence intervals for point estimates of a population proportion. If you remember in the beginning of the lesson, we also constructed a data set of race data where different races comprise different proportions of the overall population. If we wanted to make a confidence interval for the point estimates we made earlier for those proportions, we could do that using this formula. So z again, our z critical value, times this quantity, the square root of p times 1 minus p over n, which is the sample size. In this case, p is the point estimate of the population proportion that you're interested in. For instance, you probably don't recall from the beginning of the lesson, but when we generated a sample and made point estimates for the different population groups, the Hispanic population, we had a point estimate of 0.192. The underlying population proportion was 0.2 or 20%. So our sample point estimate was slightly less than that. But if we constructed a 95% confidence interval around this estimated population proportion of 0.192, we might capture the true population proportion of 20%. So let's show how we could do that. Again, we're going to use a z critical value for a 95% confidence interval, so we've already shown how to do that once. Our point estimate, p, was 0.192. The sample size that we took when we drew this estimate was a sample of 1,000. And then from that, we can calculate our margin of error using the formula we just showed. So we'll take our z critical value and we'll multiply it by the square root of p times 1 minus p over our sample size. That will give us the margin of error. Then to create our confidence interval, we just take our point estimate minus the margin of error and plus the margin of error. And we can print out our confidence interval here to see what it is. And we can see that the confidence interval we created for this proportion estimate does include the true population parameter because the true proportion is 20%, and our 95% confidence interval goes from about 16.7% to 21.6%. Now, instead of doing this calculation by hand, again, we could use some Python package functions to calculate this interval for us. So instead of doing this, we could have said stats.norm, because we're using a normal distribution in this case for the z critical values, .interval, and then we just pass in the parameters for our distribution here. We wanted a confidence level of 95%, so alpha is going to be 0.95. Our point estimate, or lock, was 0.192. And then the scale we're going to set equal to that formula, square root of p times 1 minus p over n. And if we run this, it should give us the same result and confidence interval as what we created above. So to wrap up, estimating population parameters through sampling is a simple yet powerful form of inference. Point estimates combined with margins of error let us create confidence intervals that capture the true population parameter with high probability. In the next lesson, we'll expand on the concepts we learned here in this lesson by learning about statistical hypothesis testing and the t-test. If you found this video useful, drop a like, hit subscribe, and I will see you again next time.